So now let's turn to the first law of thermodynamics, and the reason we're going to do this is because it's actually most often called the conservation of energy, the law of conservation of energy. Very important for power systems. In physics, the law of conservation of energy, or the first law of thermodynamics, states that the total energy of an isolated system cannot change and must be conserved over time. And most often you'll hear this stated as energy cannot be created or destroyed, it only changes form or only changes shape. For example, since the amount of energy output by a power station is always less than the quantity of energy in the fuel input, such as from the coal that they're burning, then the remaining energy must have been converted to something, and in this case it's actually waste heat. So there's energy stored in the coal, it gets combusted inside the power plant. Not all of the energy that was stored in the coal makes it into electricity. Well, what happened to the rest of it? A lot of it gets converted into heat. And if I add the output energy from the electricity to the output energy to heat, it equals the input energy. So it was all converted. We lose it to what we call waste heat, but it is still converted, right? As a result of the first law of thermodynamics, we can't consume energy, right? We don't use energy up. Instead, all the energy is simply converted from one form to the other. We do, however, consume fuels, one of the primary sources of energy. In an electric power plant, the fuel, coal, is often burned, converting stored chemical energy into heat, which is used to produce steam to create kinetic energy in a turbine, which in turn is used to create electrical energy by a generator. When we say the process is not 100% efficient, what we mean by that statement is that not all of the energy stored in the fuel, the coal fuel, was directly converted into electrical energy, and some of it was lost as low-grade heat throughout the process. The ratio of the useful energy output to the required energy input is called the conversion efficiency of the process. The average efficiency of electric power production plants is expressed using a hybrid standard metric unit called heat rate. So a lot of times we'll measure the conversion efficiency of power plants using this term heat rate. It's the average amount of heat supplied in thermal power plants rated in BTU needed to produce 1 kilowatt hour of electricity. The efficiency of a generator or power plant can be expressed as a percentage by dividing the equivalent BTU content of a kilowatt hour of electricity, which is 3,412 BTU per kilowatt hour. So that's the BTU content of a kilowatt hour, the energy equivalency. So the average tested heat rate for a bunch of different plants are specified here in Table 2. So we've got average tested plants for divided by prime mover. Prime mover means what type of turbine is being used, and then we've got the different fuel sources at the top. So we'll just pick a couple. First, we'll look at a prime mover that's a steam generator in coal. It's got a heat rate of 10,128 BTU per kilowatt hour. If we come over here and we look at, let's say, nuclear, a nuclear plant, it only produces electricity through the use of steam, by the way. A nuclear plant has a heat rate, similar heat rate of 10,464. So, efficiency can be as high as 90% in water turbine. It can be about 35 to 40% in a coal-fired power plant, and it can be down as low as 10 to 20% in an internal combustion engine like it's in your car. The lower the efficiency of a process, what we mean by that is the more waste heat is being produced by the conversion system. It's important to note that no system is 100% effective in energy conversion, and that there is an upper limit to the efficiency of any transducer, and some energy will always be submitted as low-grade heat, thus nullifying the prospect of a perpetual motion machine. So let's use heat rates. Let's convert those into, do an example where we convert those over into efficiencies. So let's calculate the efficiency of a power plant with a measured heat rate of 10,140 BTU. So we start by taking the equivalency of a BTU to kilowatt hour, which we said was 3,412 BTUs per kilowatt hour. And then we divide that by this heat rate that we've been given, which is 10,140 BTUs per kilowatt hour. 10,140 BTU per kWh. So if 1 kilowatt hour is equal to 3,412 BTUs, and this power plant actually takes 10,140 BTUs to produce a kilowatt, you can see why we just divide the two. We multiply that, we do this math, it ends up being 3,412 over 10,140. Once that gives us an overall efficiency of 33.65%. And my guess this is a coal plant. And it's a pretty common value, 30 to 40% efficiency for a coal-only plant.